morning a little bit, so I want to record this. All right, so you made a graph yesterday. You drew it. You put some kind of a indication of the trend. And what was the trend? How would you describe your graph that you just handed in? Linear. Linear and direct, right? Direct means when one variable goes up, the other variable goes up. So when the temperature gets higher, the volume gets bigger. And that makes good sense. You don't notice that a lot in everyday life. And I'll tell you why we don't see a big effect of that. We could see the pressure effect here. I changed the pressure inside the bell jar here, and I could get that balloon to get quite large, and I could get it to get smaller by changing the pressure. But temperature effect is something that we don't see a lot of, and I'll explain why we don't see it in a moment. So, a little picture to remind us of what our graph looked like. You don't need to draw this, but you should have had some points up in this area here. You should have then extended all the way down, and hopefully you ended up with about negative 273. If you ended up with like 280 or whatever it was, that's fine. It's not a big deal, all right? And what I want to talk about now is what you did to locate absolute zero. So I do want you to write this down. The concept of absolute zero is fairly important. And these pair of lines is the same graph that you'd drawn. I just want you to make a little sketch of it. So when you get done that particular little paragraph, you can draw a couple of little axes here. And again, this is going to be volume. The unit doesn't matter. Actually, I wanted the brackets for the unit, milliliters. And I know you have this graph on your piece of paper here, and I'll hand that back when I'm done marking it. And you can put that in your notes. But I just want a little sketch of it at this point in your notes, just to remind us of what it looks like, the important properties of our volume versus temperature graph. So again, once you have that little statement written down, volume, and then the x-axis, temperature, and temperature in degrees Celsius. And this is kind of a tricky thing for me to do on the thing, but you could probably do it. If I put down here that special temperature, negative 273, then what I would like to do is I'd like to draw a line that cuts across like this. So I'm going to attempt to draw a line here. Hey, that's not bad. We'll take that line. Now, it turns out when scientists did this with other gases, it didn't matter what the gas was. The slope was different, but hey, that's not bad. Different slope, same intercept, pretty good. So the slope was different, but the intercept was the same. That x-intercept was the same. So I'm going to do that one more just because it's fun and I'm getting pretty good at it. Let's see if I can put a third gas on here. Oh, not bad. And so essentially what I just want to, whoa, that's not what I wanted to do. It's doing so well. Now watch, if I get rid of this thing, it's going to get rid of the whole green guy. Look at, now what the heck did I do here with this stupid thing? I can't erase. I can't do anything. What did it do? Can I even write? I can. Ignore that green stripe. So, different gases. Different gases. Okay? So essentially, even though they study different gases, when you cooled them down and if you extrapolated that line down to where the volume of the gas would be equal to zero, they ended up with that exact same intercept, minus 273. And according to the kinetic molecular theory, chemists assumed that that's where all of the motion stopped. No more vibration, no more translation, no more rotation of the molecules. Complete stop of the molecules. Oh my goodness. Are we going to have that line on every single slide? That is going to be the most painful thing ever. You guys can write that. I'll freeze the screen here and I'll try to get rid of that as you're writing that stuff. What's that? No, it's not. The recording will have all of me doing all the manipulating, but that's fine. We can handle that. So that intercept was found to be negative 273. We call this absolute zero. According to the kinetic molecular theory, it's where theoretically all of the particles stop moving. We say they have 0 joules of energy. That's a J, by the way, joules of energy. So we say that's stopped. Is it possible to actually get something to absolute zero? The answer is no for a couple of reasons. One, to try to practically cool something off, like if you had some kind of super freezer, you know, could you have the interior of the freezer be absolute zero? Well, you can't, because the walls of the freezer would be connected to the outside in some way, even if you had really thick insulation. And so heat energy would work its way in through that material. Vibrations from the warm outside would work their way to the interior, which would then allow heat radiation to get into the interior. Therefore, you wouldn't be able to actually do it that way. Some students ask me, what about outer space? Outer space is pretty empty. It's pretty cold. There's no sides to outer space. But scientists have even measured the temperature of empty outer space, and they found it to be about 3 degrees Kelvin, 3 degrees above absolute zero. It's believed that this temperature comes from the heat that was produced by the Big Bang when the universe itself was formed. And as the universe grew from that hot, dense material, that hot material itself is giving off radiation. And even though the universe has been growing for billions and billions of years, there's still radiation coming from that hot explosion of the Big Bang. That's what scientists believe. They believe that's where the 3 degrees is coming from. So not even absolute zero is, not even outer space is absolute zero. Some scientists have found ways of isolating little particles in a magnetic field, like an ion, get it to hang there with the use of magnets. And what they sometimes do is they'll hit them with a laser. So as this thing wiggles back and forth, as it heads in one direction, they'll send a little laser pulse to bump into that particle and slow it down. They can get particles to get pretty slow. And I guess if you theoretically get it to stop, then you've achieved absolute zero for that tiny little particle, one particle at a time. But there are other theories that exist in physics. One's called the Heisenberg uncertainty principle, that states that you can't know for certain the speed and the position of a particle to absolute certainty. That's an interesting statement. It means if you know how fast it's going, and we're talking about tiny things. I'm not talking about cars or people or even marbles or even grains of sand. I'm talking about atoms and electrons and ions. It means that if you know how fast something's going, you really don't know where it is. you just know approximately where it is. Or if you know where something is, you don't know what its speed is. So you can't absolutely pin down the position of a tiny object like that. There's laws of quantum mechanics that prevent that. So in theory as well, you can't actually stop a particle. But this number was determined not necessarily by theory of those higher levels. It was determined by the theory of what if the volume became zero? And that was something they could easily do. Just extend that line until you had a theoretical volume of zero. And you get very close to that number of absolute zero. In order to calculate the volume of a gas using Charles' law, we must start with a temperature scale at a point where the volume of the gas would be zero. At this point, that's the only point where the linear direct relationship can be used to figure out the new volume. And that's one of the answers I would have accepted in terms of why does it have to be in Kelvin. We must start at a temperature of zero where V is equal to zero in order to have that nice relationship of if I double the temperature, I double the volume. You have to start with an absolute scale in order to do that. Let's draw one more sketch and then I'll be able to explain that a little better. So I've got another sketch that can go under this paragraph. Same as the last sketch, except I've moved the axis over, and I'm going to have this down here as being 0, but this is going to be 0 Kelvin. This is 0, and this is temperature, but now in the Kelvin scale. This again is volume in milliliters. Doesn't matter what the unit is. And I'm not worried about the different gases this time, but our line is going to head out in the same way, but now it's going to start here nicely at 0, 0. So let's have it kind of head out here. Hey, that's not bad. It's fairly straight. Again, it's just a sketch, all right? Now, with this particular representation of the graph, I now have that thing at 0, 0. If I wanted to come up with an equation for this, I could use, and you can put this underneath, if I want to use like y equals mx plus b, right, mx, oh my goodness, what a mess. If I want to use y equals mx plus b, now with this particular version, there is no b because we're at the origin, 0, 0. That means I can go back to my good old y equals kx, right? But in this case, it's going to be v equals some constant k times t. Now that little equation right there is only valid if I start at 0, 0. And it's only valid if I start my temperature at absolute 0. So I must have it in Kelvin. Now, you don't need to write any more on this graph, but let's say I had a T1 right here, and that particular T1 had a V1 right there. Don't need to write this down. Now the rate relationship works. If I double that, let's say I go T1, and I go out here twice as far, and I call that T2. If I double the temperature, because it's a linear direct relationship, what's going to happen to the volume? It's going to double. And if you take a look, I double that, and I get over to here. That's supposed to be a straight line. It's not bad. V2, I've doubled the volume. But that only works on the Kelvin scale. If I go back to this other graph, and again, you don't have to write any of this, but if I go back to this graph, which I removed all of the writing from because remember the writing failed, so I'll put it over here. Here's my line. There's my negative 273. This is degrees Celsius. I make the line go like this. That's not bad. And here I have, say, at 10 degrees Celsius, so I move that up to here, right to that point. There's my V1 at 10 degrees Celsius, V1. And let's say I double that to 20 degrees Celsius, right? So now I'm up to here. Now I'm over here. I'm at V2. If I double my Celsius degrees, notice I'm not even close to doubling the volume. Double the volume would have to be up here somewhere. And so it's not a linear direct relationship with Celsius temperature. It's a linear direct relationship with Kelvin temperature. And that's why we have to start with Kelvin in our numbers when we do these calculations. This is one of my pet peeves. You may have noticed this I find it on the radio station, sometimes on the weather, not so much. But I find this with radio announcers. I even heard one the other day. They'll say, this morning we're starting out at 10 degrees. You might need that jacket. But you won't need it this afternoon because it's going to be twice as hot this afternoon. It's going to get up to 20. You won't need that jacket. And when they say it's going to be twice as hot, that drives me crazy. Because it's not twice as hot. There's not going to be twice the heat energy in the air at 20 degrees Celsius than there is at 10 degrees Celsius. Now, if you want to double the heat in the air, you have to double the Kelvin temperature. Because the Kelvin temperature starts at 0 energy. If I had, say, 100 degrees Kelvin, and I doubled that to 200 degrees Kelvin, I would have doubled the heat energy in the air, and I would have doubled the volume. You do not double the heat energy when you double the Celsius degrees. That has nothing to do with it. Think about this. Let's say it's 10 degrees. What's that in Kelvin? What's 10 degrees in Kelvin? 283 Kelvin. If I wanted it to have twice the energy, what temperature do I need in Kelvin? 566. So I need to be here. I need to be twice out here. I need to be at 566 degrees Kelvin. How many degrees Celsius is that? Oh, I pushed the button, you silly machine. How much is it? Yep. 200. Oh, and I'm getting funny writing as well. 93. Oh, I love my computer. 293 degrees Celsius. Now I can't write anymore. Degrees Celsius. So when Mr. Radio Man says it's 10 degrees and it's going to be twice as warm, then we should expect a high of 293 degrees Celsius in the afternoon. All right? And if that's the case, I wouldn't be worrying about my jacket. I would be looking more for one of those big reflective suits that you see them wear on Mythbusters, you know, that type of thing. I'd be looking for that fire protective suit is what I'd be looking for. So it's very important. Make sure that you don't let people say crazy things like that. Okay, let's jump ahead. All right, Charles' Law. There it is right there. You can write that down. Also, this is also weather related. Another pet peeve of mine. If it starts to rain and someone complains, ooh, it's raining, right? The common thing is to say, oh, don't worry about it. You're not going to melt. I've told you about this one, haven't I, in other classes? That drives me crazy. Water doesn't make things melt. Put something in water, it doesn't melt. What does it do? It dissolves. It dissolves. Right? In order to melt something, what do you need? No. This is being recorded, by the way, TJ. Jeepers. Acid. You could burn and react something with acid, but no. What do you need? You need heat. You need heat. Right? So if the radio guy says it's 10 degrees, it might be twice as hot. If you end up getting at 293 degrees Celsius, you might worry about melting. Right? Then you say, oh, I don't want to go out there, it's too hot. Then you could say, well, what's the matter, you're not going to melt, but at 293 you might melt. I don't know. Could actually melt. So yeah, melting doesn't happen in water. Yeah, well, she was wrong. She was wrong. She says that she's melting, but she's not. She's dissolving. Well, yeah, yeah. I don't care. I'm melting. Someone should fix that. Yeah. Yep. Yeah, she was evil anyway. So we have a direct relationship. It's, again, got to be constant pressure, fixed amount of gas. That means the P is constant and the N is constant. As T increases, V increases. When you heat a balloon, the volume of the balloon goes up. That's kind of silly. You don't really see the balloon being heated. that's the other thing. That's what I wanted to talk about a little bit. We can see the effects. You know, you don't see the effects of volume on temperature that much, and that's because in the Kelvin scale, when we go from say 0 to 25 degrees Celsius, say within a season, right? You go to say like -10 in the winter, up to 25, 30 degrees Celsius in the summer. That's a small little jump in Kelvin temperature. That's not a big spread. It's about 25 degrees out of about 300 degrees Kelvin worth of temperature. So you're not really having a big Kelvin temperature change, which means things like balloons or tires or other things that contain air that can stretch and expand, they're not really expanding that much by a 25 degree temperature change. We do notice it a little bit. In the winter when it gets really cool, you may have noticed tires on cars getting a little softer, and that is a temperature effect. That also can have to do with air leaking out of it, of course, but there is a little temperature effect in the winter. You might see the tires being a little softer because it's getting cooler, but it's a very little effect. The reason it's exaggerated on a car is you've got the weight of the car on the tires, and so you can really see that effect of that little decrease in gas, in the gas that's in the tire. Okay, so V is proportional to T. That means, and we've written this down before, V is equal to some constant times T, and if I bring the T down to the bottom, there's the V divided by T is equal to a constant. And if I extend that, we've got V1 over T1 equals V2 over T2. And there's the relation equation. All right? Again, just to state, our V's can be milliliters, they can be liters, they can be meters cubed, etc., as long as they're the same. But now we have a restriction on T. T must be in Kelvin. They must be in Kelvin. All right? So we have to do conversions every time we do practice problems. And now we'll do a couple of practice problems. There's the same equation. Don't mind that. I've already done that. Practice problems. This is exactly the same as what we have been doing. We're putting it in an equation. We're rearranging. Sean, you're already giving me an answer, aren't you? I don't want to know it. But that's an indication of how straightforward this stuff is. We'll get it in a minute. If you're done writing the question, by all means, go ahead. We've got V's, we've got T's. We're looking for the new V. We're rearranging. We're getting the volume. This is about as substitute and solve as it possibly can be. I like to rewrite them. I like to write them out because if I don't have Kelvin temperature, I got to do a calculation. This one I've given it in Kelvin. V1 is 22.4 liters. T1, 273 Kelvin. V2, that's what we're looking for. T2, 298 Kelvin. V1 over T1 equals V2 over T2. I'm going fairly quickly. I'm hoping this isn't too traumatic for anybody. It's pretty straightforward stuff. V1, 22.4 liters. Oops, bad line there, but you got an idea too. 73 Kelvin. V2 is what we're looking for. T2 is 298 Kelvin. I got to move this guy over here. Multiply by 298 Kelvin. Multiply by 298 Kelvin. That's gone. That's gone. K is gone. K is gone. 298 times 22.4 divided by 273. All right, Sean. Now you can give it up. 20.53. 20? 0.52? 20.52. It looks like three significant digits. 20.5. Okay? And that's what? Liters? Liters. V2. We don't like it? Oh, that's fun. We don't like it. What happened here? You actually had yours get smaller. The temperature's getting higher, so it's got to get bigger. So you did a rearrange error. You have it smaller by that factor. Excellent. Way to speak up. What did we say it was? 24.5? 24.5. That's a good little check, right? Temperature went up. It's got to get a little bigger. And notice, again, going from, and this temperature is 0, and this is 25. Going from 0 to 25, hardly a change. Hardly a change. Now with this one, and people are starting to manipulate calculators, and that's great. I like to see that you guys just go ahead and start on the problem. With this one, right, we've got the V1, 12.4 liters, T1, 25 degrees Celsius. When I get a degree Celsius, right away, equals. Behind it, don't even think about it. I don't even need to see the fact that you're adding 273. I just want to know what that number is. What is that number? 298. 298 Kelvin is one that's pretty popular that we see quite a bit, and that's because this, remember, is standard ambient temperature, right? Remember, that's the temperature that's in the lab, that standard ambient temperature. So we use that number a fair bit. And then we're looking for a V2, and we have T2, and that is 125 degrees Celsius. And what's that? 398. It's 100 higher than the other one. Okay. So same calculation, V2 over D. Why did I start with 2? V1 over D1 equals V2 over T2. 12.4 liters, 298, V2, 398, times 398 to bring it to the other side, times 398. What do I have for V2? Yep. 16.6 liters. Okay? Now, I'm getting a sense that you're saying, come on, let's go, let's go. Give us the homework so we can get done and out of the way, that type of thing. And that's fine. I'm going to do 3 more examples, not of this one. Just relax. 1 of this one, and then 2 of what is called the combined gas law, and then you'll be able to then do the rest of the page, all right? So let's look at this one, and I want to deal with this one because of the fact that we're looking for a temperature, right? And that's a little different than the last one. Okay, I'll only do 2. Jeepers. So in this case, we're looking for T2. This would be an incredibly geeky way to determine the temperature of your freezer. Instead of just using a thermometer, let's put a balloon in it. See how small it gets. Could be done. Our thermometers are based on contraction and expansion of a liquid, but you could do it with the contraction and expansion of a gas. All right? Liquids don't follow the same rules as gases, so it doesn't work as nice as using Charles' law for a liquid, like a thermometer. But you could do it. Now, here's why I want to deal with this one. V1 over T1 equals V2 over T2. Now, I must admit, we got a pretty high average in this class, and I made a big speech earlier on about old tests and all that. But you guys as a group are mathematically pretty strong. Your math is good. I've had classes where math is absolutely terrible. And I've always had to come up with a way to help those people with the weak math to come up with getting the right answer. Now, when you're looking for something that's on the bottom of the equation here, it takes a lot of rearranging. You've got to move one up here, and then you've got to move everything else to the other side, and you've got to make sure you're always crisscrossing. For the majority of you guys, you've probably already done it, and you're already solving for the answer, and that's great. But a neat little trick is when you have a number that is on the bottom of a fraction that you're looking for, take the entire equation and flip the whole thing over. There's nothing mathematically illegal about taking an entire equation and turning it on its head, all right? So if you're looking for T2, as you are in this case, then there's nothing wrong with writing your equation as T1 over V1 equals T2 over V2. There is nothing wrong with it. You've just taken the inverse of the entire equation. And that means rearranging becomes a lot easier for those of us who don't like to deal with the complex math. Because if you do it this way, what do we have? We've got 298 Kelvin there. We've got 4.55 liters, T2, and then I have 4.02 liters, and I'm going to multiply both sides by 4.02. It means I deal with this mathematically just like the other ones I've done. I'm going to multiply it by 4.02, and I'm going to get my temperature, and it's going to be in Kelvin, but that's okay. But that is easier than rearranging on the bottom. When you rearrange on the bottom, students always get the inverse of the answer because they isolate for T2, but it's still on the bottom of a fraction. It ends up wrong every time. Unless you're really good at that stuff, then great. What do we have for Kelvin temperature? Yeah, what do you got, TJ? 263, and we actually only have 3 significant digits everywhere, so we'll stop right there, Kelvin. Okay? If you did this before I even talked about flipping the equation, excellent. That's the way it should be done. It should be done straight up. If you did it by flipping the equation, I don't care, as long as we get the right answer. What is that in degrees Celsius? Just curiosity, because I don't always. Kristen, what do you got? -10 degrees Celsius. Okay? All right? Now, at this point, I normally give time to work on the Charles law problems that are on that sheet, but you guys are an advanced group. So I'm going to just talk about what is called the combined gas law. I'm going to do one example of those, and then you can actually complete the whole rest of the sheet. I would have got to the end of that by the end of today's lesson anyway, but if I did all of the examples, you wouldn't have any time in class to work on it, but you guys can handle it. So I'm assigning the Charles law questions in the middle, but now let's, and I'll just escape out of this, and I will switch to the next PowerPoint, which is called Gay-Lussac's law and the combined gas law. There is one more relationship that we have not discussed, and that is the pressure versus temperature relationship. We've talked about pressure versus volume, that's Boyle. We've talked about volume versus temperature, that's Charles. And then there was another French scientist by the name of Gay-Lussac, and he looked at pressure versus temperature relationship. Now this apparatus works very well at looking at that relationship. We've got a pressure gauge on the top of this device. Again, it's reading about 15, so it's reading PSI. And it's got a bulb on the bottom, which obviously has some air in it, and it's been sealed. And we could take that and put it in a big beaker of ice water and get the temperature of 0 degrees Celsius and get the pressure. And we could put this in a big beaker of boiling water, 100 degrees Celsius, and get the new pressure. And with those 2 points, you could actually graph it and extrapolate it back to 0 pressure. And you can actually get pretty close to absolute 0 just from the 2 points of that. This doesn't work too bad. But we've been doing this to death, I think. I think you're starting to get the idea. And in this case, if I cool it down, what do you think happens to the pressure inside this container? What happens to the particles as they strike the wall? What's going to happen to the pressure as we cool it down? Yeah, what do you think? It's going to decrease. The particles are going to go slower. They're going to hit the walls of the container with less force, and that's going to result in less pressure. So when the temperature goes down, the pressure goes down. That's also a direct relationship, and this is also linear. No need to do graphs, no need to do the whole 9 yards. Even this part of the note, don't write this down. But the law is the pressure of a fixed gas, or a fixed amount of gas, with a constant volume, the pressure is directly proportional to the temperature. And again, it has to be Kelvin. 0 Kelvin, theoretically, no collisions with the wall, 0 pressure. Yep?
So you could put pressure on the container, temperature would go down.
If you pressurize a container, the temperature goes down? No. No.
Yeah, that's the other way around.
If you put pressure into a container, the temperature goes up? It does. But that's not, that's a special scenario. That's called an adiabatic contraction. And that gets into some really complicated type stuff. But that's the same as like taking a bicycle pump. Pump, 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 and that bicycle pump gets warm. Because as you squeeze it, it actually does give off some heat energy. And that's a more complex situation that you'll be dealing with if you continue on in university. That's a little different than this, but you are correct in that. Okay, don't worry about the equation. It looks just like Charles' law because it is the same relationship, except now we've got P's in places of V's. Now, again, don't worry about the example because the example is going to be the same. I think you get the idea, right? Okay, let's put it all together into the combined gas law. You can write the title, but don't write the paragraph. Don't write what's written down. It's not that important. Essentially, what we're saying here with the combined gas law is under normal circumstances, a regular situation like a balloon that's outside or that a kid is playing with, you have all kinds of different changes. You can have a balloon outside, the kid is being entertained by a balloon, and it's got a certain temperature and a certain pressure and a certain volume. And then that kid might have to go on a plane ride, so they take the balloon into the plane. Now, they would never let you take a balloon into a plane, but it would be cool. It would be a neat thing to see. Because as the plane takes off, you're going to have all kinds of things happening. You're going to have the pressure changing as you rise to a higher altitude. The plane's temperature obviously changes, right, because it's either cooler or they run the heaters and it gets a little warmer. So under normal, regular conditions, we very rarely have one of those variables constant. So in a real situation, you usually have two of the variables changing. Pressure and temperature changes, and we see what happens to the volume. Or perhaps the volume is forced to change and the temperature changes. What happens to the pressure? So the combined gas law puts together all of these relationships into one. And if you look at these relationships, I'm sure it's not too big of a stretch to imagine that that's what the combined relationship looks like, and that's what I want you to write down. All right? So this is the combined gas law, which means we essentially have all of our properties all in one. And if we start with a certain set of properties and we end with two different ones, we can solve for what that unknown other property is. Very easy to figure out what it is. Again, in terms of pressures and volumes, the units don't matter as long as they are the same. But for these guys, for the T's, I've got to stress this. I can't stress it enough because even when we get to a test, you forget to do this for some reason. What must T be in? Yeah, must be in Kelvin. And I'm going to give that a double exclamation mark. That's how important it is. And I've only got a limited number of exclamation marks. I can't just give them away. I'm using 2 of them here. Means it's really important. So now, a couple more examples. I was going to do a couple more, but let's just do one, right? Let's just do one. And let's jump ahead to number 3, because it's usually the trickiest one. It's the one that I throw all the twists in. Oh, actually, that isn't the trickiest one. Rats. The trickiest one is when you solve for temperature. It's on the bottom, right? Then you got to flip if you have to. But you can flip that whole thing if you have to. I thought that one was going to be a temperature one, but it's a pressure one. That's an easy one, but that's okay. You guys can solve it. So we're filling a weather balloon, 15 liters of helium, the atmosphere, pressure of 97.6. So in the end, the pressure in the balloon, 97.6. Temperature of the air is 11 degrees Celsius. If that cylinder, and when I say a cylinder, I hope we can all imagine a gas cylinder. Remember when I had the oxygen tank, we were doing demonstrations? That's an oxygen cylinder. If you've seen a propane tank for the barbecue, that's a propane cylinder. You can buy these helium cylinders too, like you can get them at Walmart. You used to be able to, right? And you can fill your balloons with it. So we're talking about that cylinder. It was a 1 liter cylinder, so it's a little guy, only 1 liter, so it may be like a little propane cylinder. It was at 19 degrees, and the question is, what pressure was inside that cylinder if all that gas was jammed into the cylinder? So that's the context for this question. Again, we gather up all of our information. I have V1, 15. I have a P1, 97.6. I have a T1, 11 degrees Celsius. And again, right away, boom, I put the equals. And what is that? 284. I got my addition going. 284? Kelvin. V2, it was 1 cylinder or 1 liter. Notice that the gas actually started in the cylinder. That was the starting point, and it ended up in the balloon. But whether they're 1s or 2s is meaningless. I always put the 1s with the first things I encounter in the question. 1 and 2, some teachers get hung up on the fact that it means before and after. It really just means condition 1 and condition 2, and what comes before and after is immaterial. What do we got? A V? Oh, I did the V. We got a T. We got a T2, 19. And what's that? 292? 292 Kelvin. And we want a P2, and this one's pretty nice one. P1 V1 over T1 is equal to P2 V2 over T2, and so P1 97.6. And I tend to lose the units when I get into these big ones because it's like I've got a lot of numbers hanging around. V1 is 15. T1 is 284. P2 is what we're looking for. V2 is 1. And T2 is what? 292? 292. Okay. Now, those of you who like to rearrange equations, that's fine. You can simply do this also by, right, I got to get all these over here. I'm going to multiply this guy by 292, and I'll multiply this side by 292, right? And I'm going to divide this side off by 1, which seems a little silly to do because it is 1. And technically, I'm going to have to divide this side off by 1. So that gets rid of my 1s. It gets rid of my 292s. And now I'm going to calculate this guy right here. P2 equals. TJ, what do you got?
1,505 kilopascals.
1,500. 05? 05 kilopascals. I guess it is 3 significant digits, so we're talking about 1.51 times 10 to the 3. That would be the proper way to do it, but I don't get too excited about you having to use scientific notation. Kilopascals equals P2. Do we like that number? Excellent. Your homework, the rest of the page, right? That entire rest of the page, and there are some textbook questions in there as well. Okay? Tomorrow we bring moles into it. Now that we've mastered the relationship between pressure, volume, and temperature, now we want to bring in moles. How do the number of moles affect these things?